All right, it's about time we get started. Welcome everyone to the HPC Best Practices webinar series. Today we're going to have a presentation about generative AI for coding tasks in scientific software by Anshu Dubey and Akash Dhruv from Argonne National Laboratory. As always, we'd like this webinar to be interactive. We use a Google Doc to collect questions, which we'll ask the speakers to answer as we go along, as time permits, and then they'll anything that they can't answer, they'll write down some answers to afterwards. So we'll have that all available after the fact. We'd also very much appreciate your feedback on this and other webinars you might have attended, and there's a link to a very short survey, just a couple of questions for that. And I'd like to just note to everybody that the archives of this webinar, including the recording, the slides, and the Q&A, will be published within hopefully about a week after the webinar is over. So you can go back and take a look at things and refer your friends to the webinar, and everyone who's registered for the meeting will receive a note when those archives are published. And I'll be putting the links for the Q&A and the feedback in the chat. I'll be monitoring the chat, and I'll try to move over questions that appear there into our Q&A document. And with that, I will turn it over to Anshu and Akash.
Thank you, David. Let me start my screen share. And thank you for that introduction, and thank you for giving me a chance to share some work that I've been having a lot of fun doing. So we start out with acknowledgements. This work is done under the SciDAC program funded by Oscar. The projects are RAPIDS, which is the SciDAC Institute, NewCove, and ENAP are both partnership projects. And this was done at NCS division at Argonne National Lab. So the motivation for us working on these topics is that whenever you're doing any sort of coding, every code-related task involves some tedium. And ideally, one would like to have an assistant who handles the tedious tasks. Now, everyone's been touting LLMs as supposedly such assistants. And, one has heard many claims about increased productivity in software development. So we thought, why should we be left behind? We want to explore the use of LLMs. And we're doing it in two scenarios. One of them was more of a necessity than the other. In that there we were supposed to do a translation of a code from Fortran to C++, and we didn't want to have to do it manually. But the first one, the one that I'm talking about, is much more for fun because I am developing a new communication algorithm, and I wanted to see how far can I push the use of LLMs in getting the code generated for it. So this presentation is about those two use cases, one for new code and one for code translation from a legacy Fortran code to C++. And in this webinar, we are sharing our experience and observations. So the first use case is development of a new code. This new code is in the context of an n-body method that is used in astrophysics, where you have a finite volume mesh and also Lagrangian particles. Particles carry mass, and the mesh carries density. When you're working in a parallel mode, which is how we always are, then the mesh is divided into blocks that are distributed among particles. So the way that this works is particles deposit density onto the mesh from the mass that they are carrying. The mesh then computes gravitational potential, forces, and acceleration and communicates them back to the particles. Then the particles then move to a new position, and this cycle keeps repeating. Now, when you're depositing mass from a particle as density into mesh, you're not just doing it on the cell with which the particle is overlapping. You're doing it also on cells that are adjacent to one where the particle is located. So the need for communication in this case arises when the particle is occupying a cell that is at the boundary of a block, as you can see here in this situation where the particle is sitting at the edge of the block boundary, which means that the cell where it is going to be deposited are going to be sitting on another block. So the most commonly used methods in these situations is that because these are finite volume methods, the blocks all have surrounding halo cells. For example, here this block would have halo cells that are obtained from its adjacent block in green. And so what the usual approach is to do the deposition into the halo cells and then do a reverse halo filling. So normally in halo filling, we get cells from green block as the halo for the blue block. But in this situation, after we've done the deposition, we would move the contents of these two cells that are overlapping actually with the green block onto the green block after the deposition is done. This works fine and very easily with uniformly discretized mesh. It becomes more complicated when you have adaptive mesh refinement, which is what most of the astrophysics codes tend to have. So now halo filling becomes expensive because what you don't necessarily have is nearest neighbor communication because the blocks are distributed based upon some sort of a space filling curve. And also, there is restriction and prolongation involved because you have fine coarse boundaries, etc. In addition to that, if you do a deposition only on the one cell of each of the target blocks, then what ends up happening is the whole deposition becomes asymmetric on the finer side of the cell, and you get spurious forces. So you need to have actually for every cell on the coarse side, you need to deposit on two cells on the finer side along each dimension. And so you have all of these complications, which means not only do you need to know where the neighbor is, you need to know what is the refinement level of the neighbor in order to do this right. So the new communication algorithm that I've devised works on the assumption that you can create virtual copies of the particle. So here, the black one is my real particle, and all of the red ones are my virtual particles. They have copied the attributes from the real particle, but they are only going to exist until the deposition is actually done on the cells and into the cells of their targets, and then they disappear. And so instead of doing a reverse halo cell fill, now we're going to send virtual particles to the target blocks instead of the halo cells. And then once the virtual particles have reached their destination, we do the deposition locally. When this happens at the physical boundary, we need additional information. For example, if we have outflow physical boundary condition, then this particle is just going to leave the physical boundary and it is not going to be contributing to the potential. So there is no need for virtual particles. A slightly more complicated situation is when we have periodic boundary conditions, because then the particles will not end up on the nearest block, which would have been on this side, but on the block opposite, on the block that is abutting the boundary on the other side. And so they actually change the destination of your virtual particle to a block on the other edge of the domain. So, and in addition to that, the additional information that is needed for AMR is the particle close to, even when it is not on the physical boundary, if it is just an internal block boundary, we need to know if the particle is close to a fine coarse boundary, and if so, which side and where does it deposit on two cells instead of one, because here on two of its neighbors, it is depositing into a single cell. Only in one of its neighbors, it's depositing on two cells. So it needs to find out where is it that it needs to take into account the fact that it needs to deposit on two cells. So I want LLMs to generate code for me, and I want to do it in a test-driven development, because it is a well-known fact that you can't assume that when you're asking the LLM to generate code, that it will generate correct code. So I need to have a very robust verification mechanism in place. So what I need to do is, in order to do test-driven development, you always have to break down your algorithms into smaller testable steps. And I have to do this here. And then, but what I will also want to do is I want to see if I can get LLM also to generate the test for me. This development is being done under Flash X, which is a well-established code. And it has a whole bunch of utilities that are available for querying the mesh. For example, whether I am on what is the boundary condition I'm working with, whether I am on physical boundary or not, what are my neighboring blocks, what are the refinement level at which my neighboring blocks are, etc., etc. But I also need to figure out how to fake those utilities for the purpose of testing the generated code. So I start by setting up my testing environment. In order to do my testing environment, I take an inventory of the constants that exist in the code. I create a smaller include file, which has all of the constants that I'm going to be including in the code. Now, except for so what I'm talking about right now is the algorithm up to the point that virtual particles are created. And in order to have the virtual particles created, I don't really need to have a full adaptive mesh. I can do this development and testing with a uniform mesh. So I create a uniformly discretized mesh with easy to inspect numbers. So I'm giving it sizing in such that those numbers, even though I'm storing them as floating point numbers, but they're actually integers. And then I create simplified versions of the utilities that are available in the code. So for the purpose of testing, I specify a uniform grid with 4x4 blocks in two-dimensional case and a 4-cube set of blocks in a 3-dimensional case. Blocks each have 8 cells in each dimension, and the physical size of my grid is going from 0 to 64, which means that each cell is 2 by 2 in 2D and 2 cube in 3D. So the numbers are not really dealing with fractions. I have a copy of the mesh on the paper, and I manually inspect the output of the test and verify against my paper setup. So this is what my paper setup looks like. I have created a mesh and I have given it a lexicographical order of identifying the blocks by single integers, and I have marked the lower left-hand corner and upper right-hand corner of each of the blocks so that when I'm getting output from the test, I can quickly compare it against this mesh that is my working copy of a physical mesh. And this is a view of the working folder, actually. So all the routines with the check mark exist in the main code, but the versions that are sitting here are the versions that are simpler versions that are generated by using AI for the purposes of testing. My test is also generated using AI, as I mentioned before. And I've even made sure that these files have the same name as the corresponding source files in the FlashX source code do. So this is what my prompt somewhat look like, is that first I've generated a grid data module, which has these variables that I've specified here. And at this point in time, we assume that I've already communicated all the meta information that I need to about this grid data module to the LLM. Now, from this point on, whatever you're seeing in red text is actually the prompt that I've cut and pasted from the file where I'm maintaining my prompt. And the ones that are in black are summarizing the prompt, are not the exact replica of the prompt that I gave to the LLM. So this one, for example, here is the exact prompt that I gave to the mesh, where I'm telling it that I wanted to write a routine called create domain that creates the mesh for me. And that routine prompts the user to specify the dimension, which means that I should be able to change it if I want to when I'm running the test. And it then returns, if the return value is 2, which means that I can specify whether I want to run the test in 2D or 3D at runtime. And I've given it instructions about the mesh to be generated for both 3D and 2D cases. I've asked it to do division into blocks as it is in my physical mesh, and I've asked it to number the blocks as it is in my physical mesh on the paper. And then these are the additional tasks I ask it to do in that I ask it to initialize the global domain with the global domain size that I've specified, and the number of blocks go into other variables, which I can be using as I develop my code and my tests. These are the prompts, most of them as is are for faking the utilities. So this is the first test program that just creates the domain and creates a makefile. And then I'm asking it to create a routine where if I give the coordinates of a point, then I get the block ID on which the point lies. And if the point lies outside of the global domain, it just returns a -1. Every time I ask it to add one of the fake routines, I ask it also to modify my main.f90 file, which is acting as my test case, so that it actually is adding the testing of the newly added utility. And I'm again verifying it by comparing it against the mesh on the paper. So then I'm asking it to be aware of boundary conditions, and I've asked it to 3 main boundary conditions that I want to account for, which is outflow when the particle just moves out of the domain, reflective when it goes back into the same place where it started from, and periodic where it goes to a block on the other side of the physical boundary. And then I'm asking it to write a standalone routines that takes block. So this is my next step, which takes in block ID as input and returns the bound box in a real array, and the delta, which is the size of the cell in a physical size, and so on. At each of these prompts, main.f90 is correspondingly modified, as I said, to exercise the new functionality. And the make file was modified to add the new files. All of this is being done with LLM. There is very little manual intervention. The generated code, it turns out, almost always had compilation errors, and some of them took me by surprise about how obvious they were, and the LLMs were not obviously eliminating them. But some of them, most of them were very easy to fix, but some of them arose from the ambiguity in my own prompt. And in those cases, I typically either changed the prompt, or in some cases, I just made the changes as I went along. This whole exercise of setting up my test framework took less than 2 hours, and that included making my paper version for the verification. So I have this entire test setup built in less than 2 hours, and now I can get on with actually designing and implementing my algorithm. Now that was where interesting things started to happen. I did this in several iterations. Actually, I think the final one that I'm happy with is the 4th iteration of the design of my virtual particle generation algorithm. And it took all these iterations and interactions with LLM to figure it out. And this is the portion of algorithm that is used for creating mirroring positions for the blocks that are turning into virtual particles. So the algorithm here is, the first thing that we need to do is we check if the particle is close to physical boundary. If it is true and it is close to the physical boundary, then we apply the boundary conditions. If the particle left the domain, there is no need for virtual particles. If the particle got reflected back, there is no need for virtual particle along the corresponding axis. And if virtual particles are needed, we create mirror positions. And again, as before, this is part of the prompt that specifies what to do. And the red portions are verbatim copies from the actual prompt. As you can see, this is where I spent in this part, for all I to pointer is where I spent the most time iterating with LLM, in that I wanted it to find a more general solution rather than enumerating every single mirror that it wanted to do. I spent several hours thinking about it, several iterations. I could not get it to do. Ultimately, I gave in and I said, okay, this is just a 3-dimensional problem. At worst, it's going to generate 7 mirrors for me, 7 virtual particles for me. So let's just do it. and enumerate it. But the first iteration, for example, that I started out with was not taking care of the boundary conditions, and it was creating the mirrors and it was doing it right. But then when I introduced boundary conditions to it, the whole thing stopped working and I had to do the iteration over design, et cetera, et cetera. And this went on for a while. I would say if I were doing it and not doing anything else, this would be 3 to 4 days of effort. As things stand, it was spread out over, I would say, roughly 3 weeks, about a few hours every now and then every week. So my observations about code generation is that even though the results are very promising in lots of ways, a lot of manual work is still needed. The prompts need to be absolutely precise, specific, and completely unambiguous, which means that it is like coding in natural language. Natural languages being very imprecise by definition, what makes communicating complicated requirements to LLM very different. And therefore, decomposition of requirements into smaller chunks becomes completely unavoidable, which means that we actually have to give more thought to the code design and componentization than you would if you, this is a good practice irrespective. But if you're doing manual code generation, you get away without having to do it upfront. When you're dealing with code generation using LLMs, you don't get away with it because the more complicated your prompt becomes, the more possibility the generator, your model, has of generating wrong code and hallucinating. In the long run, this being forced to think about your code design and componentization right up front actually makes for a more maintainable code. The other very useful thing I found is that debugging generative code directly is not always necessary. Sometimes because you can ask the LLM to also provide extensive inline documentation in form of comments, and it does a good job of it. You can very often, just by inspecting the code carefully, you can infer where you made a mistake in logic, and you can change the prompt itself. And so debugging the prompt becomes easier. And so in general, it is better to reason about the deficiency in logic through testing. I never used debugger even once in this entire process of generating my code. Other observations about code generation is that I found it easier to abandon working code when I thought of a better approach. If I was doing it all manually, and because at least I tend to introduce a lot of typographical bugs and other logical bugs when I'm doing the coding, if I have some part of the code working, I'm not going to touch it, which means that even if I think of a better design, I'm unlikely to go back to the beginning and do the code all over again. But in this case, because I was generating the code, I experiment 4 different ways of implementing before I settle down to the current one. And with every iteration, because I had given more thought to my problem, the code got cleaner and smaller. So just to give you an idea of what my earlier versions of the code looked like, this was the first set of prompts. So I gave this talk, a similar talk, to an internal audience before, and I was showing them what I was doing with my prompts and the algorithm, and this is what my prompts and the algorithms look like, which are a lot more clunky, and the design is not well thought out. So, but now I have a very succinct, very clean code. It got inline comments, and I've preserved all the prompts, which are becoming part of my repository. So with plenty of inline comments in the code and my preserved prompts, I have almost complete specification of the code, which is outstanding for code maintenance. So this was my section of the presentation. Now I could take questions now if we want to interrupt, or
Yeah, we've had a bunch of questions, so let's try to address. I'm not going to address everything we've got yet. Some of them are definitely focused on Akash's upcoming part of the presentation, but let me start with one that's fairly basic to your method. Why are 3 virtual particles for the real one? Each particle ends in 1 block only, no?
Yeah, if you have a two-dimensional problem and you're at the corner, then you have three because you're adjacent to three blocks. If you are at one of the faces, I mean, so it depends on where your particle ends up. And when you are in, when your mirror needs to be along only one axis, you have one particle. When it needs to be along two axes, you have three particles. When it needs to be along three axes, you have seven particles.
So I
Okay.
think in your
Yeah.
schematic, it looked like there were just like two blocks that were sharing a boundary. So they,
Okay.
yeah, so the schematic, in the schematic, it would be just the one virtual particle, but if,
No, well, so let me go back to the presentation. Actually, I undid the sharing too soon. So if I went back to this scenario. Yeah,
This-
okay,
yeah.
this schematic is wrong, you're right.
Yeah.
In this schematic, there should be only this, and I will make that correction.
yeah, but if the black particle were at a corner,
Yeah,
then
yeah,
you would
yeah.
have four
Yeah.
or three virtual
Yeah,
particles.
you're right.
Yeah.
That is an error. Thanks for pointing that out.
So we have real-time debugging.
Yeah,
All right. So another question. This probably will come back for Akash as well. How and how much are you training the computer to understand how you code so it can assist you? Did you submit prior code samples from your past?
no, I did not. I am not training it at all.
Okay. And then are you using a commercial AI coding tool, or does Argonne have its own coding assistant tool, or what?
Argonne has its own, but I'm using a commercial one. I'm using O4 Mini.
OpenAI O4 Mini.
Mhm.
Yeah. All right. How many attempts did you make at creating the final rather complex prompts that you show on the screen?
Like I said, I had 4 full rounds of iteration. So I will say this, that these prompts, at most 2 to 3 iterations each. And then these prompts took a lot of work. And actually, it wasn't so much that I changed the prompts, it is that I had to think through problem and its design, and I was working much more with paper and pen for designing this.
Mhm. All right, so another question. Before you write the prompts, you have to have a clear idea of how you organize the algorithm. Maybe you have a flow chart written down. You're just asking the LLM to do busy work. Is it fair to say that your prompts are your code and the LLM is a very high-level language processor?
Exactly my perspective. So in my perspective, what LLM has done for me is it has freed me from the tyranny of syntax.
Mhm. Which a lot of us would welcome being free from.
Yes, exactly.
If you end up keeping some of the code for FlashX, are there any caveats about code attribution and licensing? Does it impact your Apache 2 licensing?
I would hope not. I think what is going to happen is we are going to acknowledge that some of the code in fact, we are going to keep it. That's the whole point, right? And so we are going to acknowledge that the code is generated with LLMs and but verified, and we have a rigorous verification process for FlashX, so nothing gets accepted unless it passes the tests that we have. But yeah, we are going to keep the code. That's why I'm developing the code. Otherwise, this would be a useless exercise.
Yeah, and I'm going to ask one more question now, and then we'll move on and let Akash do his part of the presentation and come back to additional questions. So what do you consider your source code? Is it the prompts, the generated source?
At the moment, it is both. But more and more, we are also working on actually converting chunks of codes into macros and we have a macro processor and we have a performance portability layer. So more and more, our code is not going to have, or I should say, whichever part of the code that we start working with LLMs and our performance portability layer, it will not have any Fortran component to it, which means that eventually, that's my utopia, is that we will just have a code in form of prompts, in form of recipes, in form of macros, well, not even macros, in form of recipes and prompts, and that we should just be able to generate code in whichever language we want on the fly. It's not going to be a language that has a lot of structure into it like C++, but a code resembling Fortran 77 or C, we should just be able to generate on the fly.
All right. In the interest of giving Akash's time, I'm going to defer other questions. I will just note, though, that somebody has been very helpful in taking notes of the answers, and it turns out that Google labels them for me as an anonymous Python, which I thought was ironic since we're talking about C++ and Fortran and things that are not Python mostly. Anyway.
Nice.
Okay. Hello everyone, so I'm going to move on to the next part. Let's see if I can turn the laser pointer on here. Okay, so the next part of our work was looking at code translation. And for that, we started with this code, which is known as MCFM. It's a Monte Carlo code to predict processes in hadron colliders. When I started working on this code, I'm not an expert on Monte Carlo type codes. I have background in fluid dynamics, so this was a new physics domain for me. The task at hand for us was to convert the Fortran. So MCFM is a legacy Fortran code, and the task for us to convert it into C++. And the reason is we wanted to integrate this with a separate framework called Pepper, which is a GPU-based code developed with Coco's, developed using Coco's interface, and they wanted functionality of MCFM to be executed from Pepper. So this was the task at hand, and you can find, if you go to this link here, you can find the softwares that are available, like different sort of the Pepper and the MCFM code details for the software. MCFM itself has nearly 500 source files, and each file is around 550 to 20 lines. So it was a reasonable enough, each file had reasonable enough code to fit within the LLM context window. So we decided that this would be an interesting use case to explore how LLMs can be used for code translation. Initially, so when we started this, of course, everyone was excited about AI and ChatGPT. I hope everyone still is. And what we did initially was just we copied snippets of the code from the source files and would paste it into OpenAI chat interface, and we would get syntactically correct code. But our challenge was not just to have a syntactically correct code. We wanted the code to respect and adhere to directory structure, how the source code was laid out, pass through rigorous testing, and also involve, and then when you talk about testing and verification, you inevitably have to include a human in the loop. And all of our work resulted in development of this tool called CodeScribe, which is mainly the focus of this part of the talk. Let's have a quick, before we move on to the details of the code translation, let's look at the overview of MCFM code. It's similar to a lot of scientific computing applications wherein you have the source code is divided into modules, data structures, and then you can use them to run different applications. So what you can do is you can take these applications and convert some of them into tests. And that's what we use to verify the correctness of our code. And this is very important when you are with code translation, as we found out with LLMs. If you don't have a testing framework, you cannot isolate LLM. I mean, you can compile the code, but then you have hallucinations and bugs that left unidentified if you don't have a rigorous test suite. Okay, so here is an example of what code translation looks like. Second. Okay. Oh, shoot. Right. Okay. I hope you can still see my screen. Okay. So here's an example of what code translation looks like. We have a Fortran module example underscore mod that is converted to C++ header and source file. It is important to note that here we are only focused on producing Fortran-like C++ code. We are not focused on producing idiomatic C++ code and avoid using classes, because what we ultimately want is MCFM to become an arithmetic-only library. Just so the translation process is more straightforward than like if we had classes. See, if we had to convert Fortran modules into C++ classes, because that would become more complicated. And for the purposes of this initial study, this is what we focused on. Another thing I would like to point out is that F2C was an available option, but it does have limitations. First of all, F2C cannot crawl the directory structure and identify different dependencies within the source code. So let's say if you're dealing with a source file, which is referencing code from modules that are located elsewhere in the directory, F2C doesn't have that capability, and we wanted to introduce that capability into our code translation tool. So with all of that, we decided that, okay, let's explore LLM, let's write. And we'd like to note that CodeScribe is not a pure LLM-based translation tool. We use LLM as a component, but a lot of the rest of the part involves scripting and pattern identification that is more directly written source code from the developer, which is me. Anyway, so going back to this example, we convert this Fortran module into a C++ namespace. We replace use module statement with include statements, basically writing Fortran in C++. And that's what we have for the modules. The other component is converting Fortran subroutine to C++ following similar convention, replacing the use module statement with corresponding header files and namespaces. And converting Fortran use statements to using namespace statement. And then there are, and also to note that we are not using Cocos right now. The goal was to convert the code into C++ and then add another layer of LLM translation to introduce Cocos related syntax in there. Okay. Our conversion process is as follows. We have a driver C++ code, which you see here, over here, that interacts with the core Fortran code base via Fortran C interface. So we first identify groups of modules and data structures within this core code base that are interdependent on each other, but independent of the source code otherwise. And what we do is then we convert that into the core C++ code base, and then write a corresponding Fortran C layer so that it can interact with the rest of the code base, but then interacts with the driver code directly. And then we perform tests on this converted code, and we slowly move to the rest of the Fortran code base and replace it with the entire C++. Here is the overview of CodeScribe. We use CodeScribe to accelerate our workflow. We start with, so the blue components that you see here are automated. They are handled by CodeScribe. It has some component, for example, and I'll go over the stages in detail there, but it's a mix of components that involve scripting and LLM use. The red components that you see here involve developer interaction. So we start with the core Fortran code base, and we follow different stages. And I will describe these stages in detail in the next slide. So the first stage is index, which serves as a reference to determine where different things belong in a directory tree. So you take the Fortran code base, you index the code base, you understand what the directory structure is like, what is contained in each file, what modules, subroutines are present in each file. Then you perform a neural inspection to identify dependency between the modules, identify patterns in the source code, and you use this knowledge to build prompts, which are the chat completion templates, which are described in the next slide. And then you use that knowledge, and then there is a stage called draft generation, which is basically a scripting. This is an additional data point for the LLM so along with these prompts that we develop, we add additional data point. I'll go over the details again in the next few slides. And then we combine that and perform a neural translation that generates the corresponding C++ and Fortran C interface files, and which go through testing. If the test fails, developer either manually edits the files or updates the chat completion prompts until we can merge everything into the C++ code base. All of our code is open source. You can find it here and on GitHub. And if you are interested in applying CodeScribe to your applications, I may be able to assist you there as well. Okay, so now I'll provide a brief overview of different commands. The index command handles code-based indexing. So it creates these type of YAML files, as you see in this cartoon here. The YAML files contain path to the directory, file names, and corresponding modules. And the purpose of this is we found out, so if you were to just copy a source code and put it into ChatGPT-like interface, if the code is referencing external functions that are located or functions that are located elsewhere in the source code, ChatGPT would try to extrapolate the meaning of those functions, right? And it would create unnecessary hallucination in your generated code. So what we wanted was to avoid this hallucination and create this database that can be referenced during the prompt itself. So when you are doing a code, when you are translating code that is in a file and it is referencing an external subroutine, you just provide a prompt that this is located in this directory, no need to translate it. And this indexing helps us to do that. And also I would like to note that these commands sort of came about through our experience as we were trying to dissect our conversion process into different stages. We identified different things that need to be done in sequence. So you actually have to index your source code first, and then you move on to inspection, where you use LLMs to answer queries for a set of files, right? So, and I would like to note that all of our interaction with LLM is through APIs. So either we use local LLMs using Hugging Face API, or we can use OpenAI or Argonne's LLMs. Argonne's LLM is called Argo through Argonne specific API. So we use so what we do is we take a set of source files and we we pass a query on the source files. And we trigger the LLM through its API, and it gives us answers. Okay, these source files share a similar pattern. These source files are interdependent on each other, and that's how we build these relationships between source files. And then what we do is we use these relationships and these patterns to create these type of chat completion templates, which you see here. The template contains a conversation, and this is a fake conversation. This is not generated by LLM. This is a conversation between a user and an assistant, where the user starts describing the rules of conversion and then provides a dummy example. And then we use this conversation and supply it to LLM to actually do the translation. So here is I hope you can see, this is what actual slow chat completion template looks like. So you start with the user describing different rules, right? So this is a module that the user wants it to convert, provides all the examples, how to treat. So we treat multi-dimensional array using a container class in C++. So we don't really change the memory layout of the arrays. That makes the conversion process very easy. So you tell, okay, replace the real array in Fortran with a container class object. So you go through these, and then assistant says, okay, I'm ready. And then you actually provide a concrete example, which is lightweight. It's not like a big example. So you say, okay, convert. And then we enforce LLM to embed the code inside these elements. So you can see source elements, and then C source elements, and F source. So at the end of the day, so this is what we teach. And then we say, okay, now convert the following code. And then we append the actual code. And then LLM does the same thing. So what we can do is at the end, we can extract the code from the elements and plug it into a file. The other part is the draft command. So draft command is used to create these files that are called, that have the scribe suffix. So it is important to note that what we saw previously, which was a chat completion template, chat completion template act as a general prompt for a set of files that follow a pattern. And then the draft command creates these scribe files that are very specific to the file. So they provide an additional data point to the LLM. And it converts basic, it does simple basic conversions. It provides, and also does simple basic conversion for multidimensional arrays. So we can look at an example here. So over here on the left, you see this is a Fortran function, right? And then when we run the draft command, is a simple Python scriptm command that understands, okay, this is an external function. So it uses the index command and identifies the external function and just provides that as a prompt. It converts these use modules into including the header files and namespaces. It converts multi-dimensional arrays to a Fortran type container class in C++ and leaves the rest of the code untouched, right? So the LLM can use this draft as a template and then do the actual C++ code conversion. And this one was produced by the LLM on the right here. So the overall workflow is like this. You take the chat completion template, you take the file name .f90, which is your source file, you take the scribe file, which is the draft file, you combine them together, you run it through a neural translator, which is triggered through an LLM API, and then you produce the file name .cpp, and then file name underscore fi.f90. So this file name underscore fi is the Fortran C layer, right? Eventually, this file would go away when the entire code is converted to C++, but we need to create this file for compatibility and testing, right? We have a paper out now. You can find the paper here. There is an archive link, and it is also published in the proceedings of PASC 2025. This is our process. Okay, so performance. So we did experiment with different LLMs. As you can see here, we used GPT-4, GPT-3, and some lightweight models, CodeLlama and Mistral. So in terms of performance, what we were focused on, like how much productivity it actually introduces, how much time does it save for a developer. So what you see in this graph here is the time it was required by the developer me for reviewing and testing each file and integrating it with the core code base, right? So the way I do this process is I convert a set of files into Fortran, from Fortran to C++, then I calculate the time it takes me to review these set of files and run the test suite and integrate into the C++ code base. And then I take that total time and divide by the number of files that I was operating on and calculate this time. And you can see that GPT-4 and 3 GPT models are performing very well because of their higher parameter count. And then the local models perform poorly. But this introduces an opportunity to fine-tune these local lightweight models because these models were not fine-tuned for this specific task to understand the specific instruction context. So if we were to fine-tune it, maybe this time would improve. So far, we have seen some good results. Human intervention is important, but it has helped us reduce our time to completion. It is good for developer productivity. Model fine-tuning can help, and we are currently in the process of exploring how this can be made more general for scientific computing code bases. I think fine-tuning would be a way to create a general model that can be used for code conversion problems for scientific computing codes. And another thing that we would like to also see if we can reduce human in the loop, or like if we can improve the tediousness that is introduced on the developer by doing this human in the loop aspect, where we can automate some of the things, like maybe use like an agentic framework, where if we get errors in the test suite, we can use those errors to update the generated code without having the human to change the prompt manually. And I mean, of course, we will never eliminate human in the loop because we want a human to stamp the correctness of the code. So that will always be there, but how we can further improve the synergy between human in the loop and the auto generation part. So that's something that we are exploring. Yeah, and with that, if there are questions, we'd be happy to take them.
Thank you very much. There are loads of questions. I don't think we'll get to them all, but I will try to ask a few. I'll also note that there's been a lot of interaction. Anshu's been answering some of the older questions in the chat, and some people have been responding. So there's a lot of activity there. If you're not following, you might be interested. So here's a question that I think applies to some extent to both of you. Have you tried optimizing the code for HPC architectures using specific libraries?
So I would like a clarification on it. Is it asking about using without the use of AI or with the use of AI?
I assume in the context they're asking about with the use of AI.
No, then we have not tried it at all.
All right. So was your use of the coding assistant for the Argonne exascale system? I'm desperate to learn best coding practices for this new system.
Well, Argonne's exascale, so maybe Aurora. So is this Aurora specific question?
I think it could apply to either of you.
No, well, what I meant to ask was, is this question specific to using the Aurora computer?
Yeah, I think this is somebody who's interested in Aurora.
Okay. I mean, I think currently we are not using Aurora for any of this work.
So the short answer is we do not have experience to answer this question because we have not tried that. There are other efforts within Argonne that are trying to do this, and if you're interested, we can find out and connect you.
Yeah.
Yeah, also comment that Argonne, if you're just interested in using Aurora and the best practices for using Aurora, separating out from the AI aspects, Argonne, ALCF itself runs an extensive training program, and we'll put a link to that in the answers as well.
Yeah.
So there's lots of recorded material and regular trainings that are taking place on different aspects of the system that might help. Yeah, Anshu's getting ahead of me. Why did you decide to apply this coding assistant to Fortran?
Because our code is in Fortran. Very simple.
Yeah, you started the Akash's activities started with a Fortran code that needed to be translated to C++. That was the problem you were given, right?
Yes. Yeah.
There's a couple more questions about licensing and intellectual property, and I'm going to skip over and we can do those in a written form. Using the LLM to write code is supposed to save time and effort, but after the LLM gives us a code, it may or may not be right. We still need to go back and fix things. Sometimes learning somebody else's code, in this case the LLMs, is almost as much work as writing the code ourselves. In your experience, is the LLM really saving you time and effort? And I think that's a question for both of you, different contexts.
For me, definitely. A huge amount of saving. And I will tell you this also. For example, a lot of the, so like I said, whenever I'm writing code, I inadvertently introduce bugs, which I take a lot of time cleaning up. And at least when I've got LLM generated code, I don't have typographical bugs usually that I have to spend my time figuring out. And the second one is when it doesn't take me 1 hour to write a different version of the test, I'm much more willing to do it than I would if I had to do it otherwise. And the third one is that, if you're asking it to do routine functions that it has seen before, like the kinds of utility functions that I was generating for Flash, it just gets them right the first time. And so it definitely, so putting together my testing harness really saved me a ton of time. And I don't think if I had determined it to be as easy as it proved to be, that I would have gone ahead and created a separate test harness for myself at all.
And for me, I think when I started, like this was a new code for me, so I wasn't very familiar with the MCFM code. When using AI, what AI helped me is when I was trying to solve LLM hallucination and bugs, I was solving specific things that helped me understand the code better. Because instead of like reading the whole code and identifying what is going on with the whole code, I can look at a specific thing and trace it in the source code. And that helped me actually understand the source code better. So I would say in my situation, AI was helpful to learn the code itself.
It basically turned it into small enough chunks that you could digest.
Yeah. So like if there is a file that is, test suite is working initially, and then I change a few files and it's not working, then I only have to focus on those files. And then I can understand the code base efficiently that way. Because then the task is in the small files. Yeah.
A couple of questions here for Akash. There's an existing utility F to C. Did you ever think of using that? Have you compared the LLM generated code with using a tool like this?
So I haven't compared F2C with CodeScribe yet. I think the challenge with F2C, as I mentioned in the beginning, was the directory structure. I think we wanted to embed the directory structure and have the translation process respected. I think it would be good to do a more robust comparative analysis between F2C and CodeScribe and report that. So yeah.
And another methodology question, code translation problem seems to me that it could be handled by compilers, i.e. code rewrite rules. Do you think it makes more sense to implement this kind of capability in a compiler rather than LLM?
I would say it's possible, but does anyone really have the incentive to do it? And that's where it comes down to, is that if you can get reliable code translation done using LLMs, why would you invest a whole lot of effort into developing a compiler-based technology? Though, of course, the compiler-based technology would be more reliable in general, and you could then do it. But you know what? I've been looking for years for compiler-based translation options, and I haven't come across many, so there must be a reason why there aren't.
And then speaking to the point of IDEs, this field is rapidly evolving, right? There is no reason to not believe that in a few months there will be IDEs that can use LLMs itself to help you translate your code base directly. So.
But I will also say this, that there are, in the scientific computing world, there are many cottage industries going in manual translation of code from Fortran to C++ just to become compatible with Cocos, so that they can use the portability. I don't know why no one else has thought of a solution, because it is a big problem, so it must not be an easy solution to implement.
Okay, we are at the we are at the top of the hour, but let me do one more question live. So rather than use LLMs, which don't have reproducible output, why not use existing code generation technology such as domain-specific languages? So maybe you can both address your thoughts about that.
I don't know of a general purpose domain specific language that can do the code generation for you on arbitrary piece of code the way that LLMs can. So anytime that, in fact, people have tried to use domain specific languages and even embedded domain specific languages, and by and large, they have abandoned those because by the time you get a domain-specific language up to the point where you can do a code generation with it, it begins to look like a natural language and it has as many features, and your code becomes as complex as that. So, and again, it doesn't free you from the tyranny of syntax. That's my biggest plus for LLMs. But you do need to have robust verification.
Yeah.
Yeah, I'll just comment a little experiment that we did with generating OpenMP tests and using ChatGPT, just the standard commercial version. One of the most common problems in the Fortran generated code was that it was trying to declare variables in places where Fortran doesn't allow it, but C does, which we thought was a little bit interesting. That there's a case where it gets the tyranny of it suffers from the tyranny of syntax.
Okay.
And Akash, I didn't know if you wanted to address that question as well from the translation viewpoint.
Can you repeat the question, please? I was answering.
DSL.
Yeah, so DSLs
Okay.
versus LLMs.
I don't think DSLs would address that problem at all, actually. Because
Yeah,
that is,
Yeah.
I guess that's true.
DSL is more relevant for generating
new code.
Yeah.
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 And I'll just comment on Anshu's use case. I think what she was doing was exploring a new algorithm in this particular case, and so that would be, to my thinking personally, it would be kind of the step before you design a DSL. If this is something you're going to be doing a lot, you might want to, figure out how a DSL could help you there, but you'd have to do some exploration first.
Yeah.
All right. So we are beyond time. I want to thank everybody who's participated. We had a lot of interest. We had a lot of great questions. We're already well on our way to getting answers to those questions. And as soon as we get everything completed and posted, we'll send out an email so you can all go review everything and share it with your colleagues and friends. And thank you very much to Anshu and Akash especially.
Thank you.
Thank you.
We enjoyed this.
Yeah, I was just answering some questions, so I think I've answered all the questions on the doc. Okay.
Okay.
Bye.
Thank you all.
Bye.